I think I am live now. Can anyone confirm if audio and everything is fine before we get started? I was able to solve all problems, so I will definitely discuss solution of all the problems. And like that's where we are. So yeah, probably let me add this same link on Atcoder and give me 2 minutes. We will get started. Like people in the chat, like how many problems were you guys able to solve today? Okay, I think I am live now and I should be audible as well. Like I will start from discussing problem A and then keep going on. Like the first problem says we are given two integers a and b. we have to count the number how many different x exist such that it is possible to arrange three integers a, b, and x in some order to form an arithmetic progression. Definition of arithmetic progression was also given to us. So like the main idea was like probably the samples give away much of the solution idea for this problem. Like in one of the sample the answer is 3, in some and sample the answer is 2, and in some sample the answer is only 1. And like these were pretty much the answer. Like the answer was always up to 3 only, and there were many different cases over here. Like for example, the like what do we mean by arithmetic progression would be the first question someone would have on this problem. So like for example, let's say like let's look at 3 and 3. So it said that like only with x equal to 3 we can get an arithmetic progression with common difference 3 0. Like in general, the arithmetic difference is defined as a sequence characterized by a, the first term, d, common difference, and l equal to length. So like the length is fixed, which would be 3 in this case. The only variables we have is a and d. And arithmetic sequence looks more like a, first term is a, second term is a plus d, and the third term is a plus 2d. So like, or basically, let's to ignore some confusion here. Let's say like the first term is a, second term is a plus d, and the third term is a plus 2d. So like the only variables we have over here is like we can probably put a here, let's say, and let's say b here. That can be one way. We can put b here and a here, but you can probably verify that in both of the cases the common term would be same. Like it asks us to find like what can be the different choices for the third term. Another possible option can be a, b, and the third term here, and like probably the another choice would be a difference here, b, a, or something like that. Like you can probably have 6 terms here, and you can probably verify that a lot of x values would be same over here. Like this case will give us the same value of x, a, b, and something. Like these two cases should give us the same value of x, and these two cases should also give us the same value of x. The main idea would be like we can have a, b, and a plus b by 2 as a term if this is an integer. Another term could be, let's say d is the difference between a and b. Then the next term we can have would be a, b, and b plus d. And another sequence we can have would be a, b, and a minus d. So like these would be the only 3 choices we would have, and we can probably verify based on different cases which term it would be. If a equal to b, you can probably notice that all of these 3 values of x will give us the same value. This, and this would be same. If a and b, otherwise we can always get these two different values here. And if a and b are either both odd or both even, then we can also find a midpoint there. So the answer would be 3 in that case. Jumping on to the code for this problem. So like in case n equal to m, we just print 1. If sum of n plus m is odd, we will not be able to find the midterm, so C out 2, otherwise C out 3. And this was essentially the solution for the first problem. Any questions on this one before we move on to the next problem for today? I would be back in a second. Okay, then I will probably move on to the next problem. Piano 3, it says Takashi has a piano with 100 keys arranged in a row. The ith key from the left is called key I. He will play music by pressing n keys one by one. For the ith press, he will press key AI using his left hand if SL equal to 1 and his right hand if SL equal to 1. Before starting to play, he can place both of his hands on any key he likes, and his fatigue level at this point is 0. During the performance, if he moves one hand from key X to key Y, his fatigue level increases by Y minus X. Conversely, the fatigue level does not increase for any other reason than moving hands. To press a certain key with hand, the hand must be placed on that key. Find the minimum possible fatigue level at the end of the performance. Like, I think it would be beneficial if we look at the sum of the samples here. Like, let's look at one of the sample and see what's happening here. First sample says from the left hand press 3, from the right hand press 6, from the left hand press 9, from the right hand press 1. The main idea is your starting key should be the first key you should press with left hand, and first key you should press with left hand. So initially your left hand would be at 3, right hand would be at 6. You won't do anything and you can directly press those keys here. Next time when you encounter 3, like the previous key which was pressed using left hand was only 3. So you have no choice but to move from 3 to 6 here with the cost of 6. And then when you are on right hand, the next is from right hand press 1. You know that the previous right hand key was 6. So you have no choice but to press it, move from 6 to 1 with cost 5. And total cost here would be 11. Yeah, like basically that's right. Start with the first left hand. First key you press using left hand, press your left hand there, and first key which you press using right hand, press your right hand there. So I took an input, like I created basically two vectors of length 2, like basically left and right hand. Like if you press using left hand, let's put it in this vector. If you put it with your right hand, press it in another vector. Now solve independently for both of these vectors. Now like for array A is the key you should all be pressing using single index only. So if you start with the first index, like if you don't press any key using this hand, you should dodge the 0. There is no fatigue here. Otherwise your current key is 0. Current answer is 0. First your answer increases by wherever your previous key was, and then your hand moves to that key. And like that would give you the count for this particular hand. If you count for both of the hands, you will get the final. Any questions on problem B before you move on to problem C? Okay, so the problem C says you are given a sequence of n positive integer a1 to an. Find the number of pairs of integer L and R that satisfy such that number of subsequences of AL to AR forms an arithmetic progression. A sequence x1 to xn is arithmetic sequence if and if there exists an integer d such that xi plus 1 minus xi equal to 3. In particular, the length of sequence, in particular sequence of length 1 is always an arithmetic progression. So what you know is like if you take length 1 you will get a sequence. If you take length 2 also you will get a sequence. Like length 1 is always a sequence, you can choose any common difference. Length 2 would always be a sequence because for two number whatever their difference can be a sequence. And for length 3 and onwards you would need probably higher number there. So the main idea for this problem was, like, let's probably look at one of the samples first. Like for each index, let's maintain like what is the maximum common arithmetic progression we can get. Like for example, 3, 6, 9, 12, 15. Let's say this is one of the sequence we have. 2, 4. You see, like you can always start from, you can always get a sequence of length 1 from here, and you cannot get more than that because you cannot move backward. For this, like you can get always the arithmetic, you can get 2 arithmetic length at max 2. If you take just this element, this is an arithmetic sequence. If you take this as well, you will get arithmetic sequence with difference 3. And now you see here, like if you take just this element, you would get a sequence of length 1. That's fine. If you take these two, you will get a sequence of length 3, difference 3. And now notice that this difference is also 3. So you can also expand like whatever the arithmetic sequence you got plus 1, 3 here. Now when we come here, like you see the difference of these numbers is also 3. So like length 1 also works, length 2 definitely works. And for length 3 onwards, like whatever the 3 sequences you got from back, you can also extend the same sequence here. So you can get at max 4 elements if you if this is your final element. Now this difference is also 3. So it will turn out you can always get this element. You can take this element to get length 2. And because this and this difference is also 3, you can also extend this sequence to get one more element. Now here the difference is 13, minus 13. You can always take this element. You can also take this element, but you won't be able to even join 12 here. Because here the difference is minus 13, here the difference is 3. So the maximum element you can take from here would be 2. And here the difference is 2. The answer would again be like you can take this, you can take these two, but you won't be able to take any more. So the answer would be 2 here. Let's probably expand this sequence a bit more. Let's say we have 6 and 8 here. This difference is also 2. So you can definitely take this, and you can always extend the previous sequence as well. So like the main idea is like, look at the difference from these two elements. If this difference is same as this difference, increment this answer by plus 1, otherwise mark answer equal to 2. And like this was the only idea. So I will probably show a bit code here. Like maximum length you can get with index 0 would be 1. And maximum length you would get with index 1 would be 2. Like let's also, like notice that answer is less than equal to 2. So like for if we have only one element, that only element would be our answer here. If n is 2, the answer would be 3. You can either take one element each, or you can take both of the elements. Otherwise, we start from answer 2. If aj minus 1 equal to aj minus 1 minus aj minus 2, then max length j would be 1 plus whatever the maximum length we got previously. Else maximum length starting with j would be 2. Now we want answer for all of them. Like now keep a track of like how many element you can maximum take from each of the element here, and that would be our answer here. Any questions on problem C before we move on to problem D? Yeah, like NC2 etc. was the idea I did in the contest, but I found this a bit easier to explain. Okay, I will move on to problem D then. Problem D says bonus EXP. Takashi will encounter n monsters in an order. The ith monster has strength AI. For each monster, he can choose to either let it go or defeat it. Each action afterwards award him experience points as follows. If he let go a monster, he gains 0 experience point. If he defeats a monster with strength X, he gains X point. If it's an even number defeated monster 2, 4, etc., he gets an additional experience point, X experience point. Find the maximum total experience points he can get from n monsters. So what it's saying is like you take a sequence of, probably let me just take an example here. So like let's take this example. 1 second. C, okay, D. Where is problem with 1 second? So for example, we have 1, 5, 3, 2, 7. It says in the optimal order we should take these monsters. So number of points you would get, first time you would defeat one monster, you will get 1 point. Second time you will defeat monster 5, and for every even monster you get double points, so you will get 10 points here. Third time you will defeat monster 3. Fourth time you will defeat an even number of monsters, you will get double points here, so 14. And the answer here turns out to be 28. So basically for even monster, reward doubles. So the main idea first here would be DP I length count. Maximum reward we can get. We can get after processing first I monsters. I monsters and fighting with the with count monsters. Overall, like this DP would have order n square time complexity, but probably let's first implement it before trying to optimize it further. This should definitely get some value. Let's probably keep it one base indexing. You fight with 0 monsters by taking up to 0th monster. That is 0. For LL I equal to 1, I less than equal to n, I plus 1. And let's say like for LLI, previously taken monster count is like current taken count is 0. If you don't do anything, your monster count will still remain 0. First current cost, current reward, let's say. If it's an odd monster, you get AI. Otherwise, if it's an even monster, you get 2 times AI. And the value here would be DPI If you first do nothing, you have two choices: either take the current monster. If you don't take the current monster, then like this would be your report, like doing for nothing. Or if you take the current monster, then like you would have previously defeated this many count of monsters plus the current reward you would get. And the maximum answer would be, when you have processed everything, taken count can be from 0 to you have processed all the elements and now you are also iterating on the taken count. And like this solution is order n square, will definitely get a TLE, but let's submit it. Like this was the main idea. First thing first. Okay, runtime error might be because of memory limit, I believe. 2E5. We won't be able to create n square array here. Like memory limit exit is not a verdict here. The next important observation was current event only depends on whether if the number of elements taken so far is odd or even. So instead of an order n square array, we can now define a DP like this. DP odd I means we have taken odd number of elements in first I elements. DP even I denotes we have taken even number of elements in first I elements. Now when you want to take I and total even number of ith element and total even, then you should take odd number of elements from first I minus 1 element. And like this was the main observation required over here. Similarly, we can go for odd and even. Yes, runtime error is due to MLE. Like Atcoder does not support memory limit exit. So the next idea would be DP odd n plus 1 element minus infinity cost. DP even n plus element minus infinity cost. Now you see, like you take 0 elements up till 0th element, so their cost is 0. If you do nothing, then DP odd remains the same cost. Or if you take even elements up till I minus 1 and then odd element, this would be your final cost over here. And if you want to take even elements up to ith element, then either you can do nothing over here, or you can take odd elements up to I minus 1 and take 2 times the current element cost here. Now your answer would be max of, if you take odd elements, this, if you take total even elements, this, and you print the answer here. And like this was the next idea for this problem. These two optimizations: first, how to solve it in n square, and then noticing that we only need second element length is odd or even, not the actual length over there. Any questions on problem D before we move on to problem E? Wait 1 second, YW. Okay, this should be I minus 1. Sightseeing tool says there are n islands, m bidirectional bridges connecting two islands. The island and bridges are numbered from 1 to n and 1 to m respectively. The ith bridge connects ui and vi, and the time it takes to cross in either direction is ti. So basically one undirected graph where each edge has a weight somewhere. No two bridges connect an island to itself, but it is possible for two bridges to be directly connected by more than one bridge. You can travel between any two bridges using some bridges. You are given some queries. So answer each of them. The ith query is as follows. You are given ki distinct bridges b1 to bki. Find the minimum time required to travel from island 1 to n, and we should use each of these bridges at least one. Only consider the time spent across crossing bridges. Like these bridges includes all the bridge on your part, not just these ki bridges. You can cross the given bridge in any direction and in any order. One important constraint was at any point of time we will have only 5 bridges that we need. And n was up to 400, but m was up to 2e5. So the first thing we need over here is, let's see how does an optimal structure look like. Let's say we want to go with bridge 1, bridge 2, bridge 4 and bridge 5. So we will visit these bridges in some order, right? We will start from node 1. We will go somewhere and then one end of bridge, say bridge 5. Then we will travel across bridge 5. Then we will travel some another bridges first. Then let's say we travel across bridge 2. From one end of the bridge 2 to other end of the bridge. Then we will travel something. And then we will say move to one end of bridge 1 and come out with other end of bridge. Then we will travel at some path. 1, 2. Then let's say we will go to one end of bridge 4, cross it, and then when we will go back to n. Like you see, like this would be the idea how this crossing would look like. One thing was, since it was up to 5 and k was up to 5 only, we can try all k factorial permutation to cross these bridges. And then you see, like there can be two ways using which you can cross the bridge. You can directly do either 2 to the power 5k over there, or you can probably maintain a dp here. First thing we need is, for every node, pre-compute distance of v to u. The minimum time you need to go from u to v. It does not matter like which bridge you take. There is no restriction on the bridge. For this, you can use traversal. Like I hope I am writing the spelling correctly. You can find some content about it in user guide. So yeah, like you can find some content about it here. So this in order n cube finds the distance between each pair of vertices. M is up to 2e5, but order n cube works. Or you can probably use Dijkstra as well. Just keep, instead of keeping 2e5 edges, just keep only one edge from u to v, and that should work too. So my idea was, like, we can first fix a permutation to iterate. Now let's say like bridge 1 goes from 2 to 3. This would be the first bridge we will visit. Then the second bridge, let's say we visit from, would be 5 to 6. And the next bridge we visit is between 3 to 4. And then we will go to vertex 10. And this is where the vertex is. Now my main idea was, like, when we are crossing the first bridge, we will either be here. We will first go from 1 to 3 and come back to 2. or we will go to 2 first and then come back to the other end. So I can keep two variables as a DP, like what is the minimum distance to reach 2 by going to 3 first to reach here, and what is the minimum distance to 3 by going via 2 first. This ensures I have visited vertex 1 first and I have two variables here. Next time when I am going to the edge 6, the way I can go is either I can go from 2 to 5 or 3 to 5, whatever minimum distance I have already computed, and then go via this edge to go to 6. Or I can go from 2 to 6 or 3 to 6 and then follow this edge to reach 5. And like essentially this is what I was doing here. Now when I want to go to 3 here, the way I can do is either I can go from 5 to 4 or 6 to 4 and then follow this edge to reach 3. Or I can go from 5 or 6 to 3 and then go via this edge to 4. And then at last either I will go from 3 to 10 or 4 to 10. Every time when I am making jumps like this where I have no restriction on edge, I'll just look at the minimum distance which I have already pre-computed. And like this ends up being the solution for this problem. So all the edges as input, like minimum distance for each of them. Distance to reach from I to I would be 0 only if we have no restriction on edges. Like my spelling might be wrong, but the resource I have shared is one Floyd-Russell sorted fast finding algorithm. Or you can even in fact do a Dijkstra n times, just ensure that the number of edges are probably, like you remove all the, if there are multiple edges from 1 to 2, you only keep the one with edge distance 1, minimum distance. So take all the edges as input. Now you have edge from U to V with weight 5. So minimum distance from U to V can either be, or V to U would be whatever minimum length we have found so far and weight W. And like this 3 lines loop is Floyd-Russell algorithm. And it, once this iteration is complete, every edge from D U to V will have minimum distance from U to V. Now take K as input, all the edges as input, sort all of them and try all the permutations to visit these edges. Once you have picked a particular order of iteration, like what I say is like I maintain 2 paths to give both of the reaching both of the endpoint. Initially I would be at node 0 and I would reach it with distance 0. Now for the ith edge, U is this, V is this, weight is this. So like I first say, like the minimum weight to reach U would be like the current edge path, and from one of the previous endpoint to go to V, like whatever minimum distance was to reach one of the path and that part to go to V. Or for the second edge, like endpoint in the previous algorithm we had, whatever distance was traveled there and minimum distance from that endpoint to V, like go to V and then you go to U. Similarly, minimum distance to reach V would be whatever previous path we have traveled from its one endpoint go to U and then travel it to V, or the second endpoint we had. Just update it, and at last you would have the last edge and you have visited one of the endpoints there. So whatever distance was traveled there, go to N from the other endpoint. And whatever distance was traveled, go to N from the other endpoint, and keep trying all 5 factorial permutations, and this ends up being the solution for this problem. Any questions on problem E before we move on to problem F? Yeah, Floyd-Russell would be N cube. So like problem F says there is a grid with H rows and W columns. Let Ij denote the cell at ith row from top and J column from the left. There are n coins on the grid. The ith coin can be picked up by passing through cell Rici. Your start at 1, 1. Your goal is to either move left or right and reach H, W while picking up as many coins as possible. Find the maximum number of coins you can pick on one of the paths that touches it. The important constraint was generally we have grid problems like this. We have a constraint on n into m, like the total size of grid to be 2e5 or not. But in this particular case, it says like both the lengths can be up to 2e5. So if it was h or w were up to h into w were less than 1e6 also, you could have probably used the standard DP. But this idea does not work. But one important constraint was like the number of special cell is up to 2e5. And all the pairs are distinct etc. Like this ends up being like there is a problem on code forces, giant chess or Girald chess. Yeah, like this I think so. Yeah. You can probably code this one as well. I don't think NAPSAP type of things works. Yeah, like you should probably try out this problem as a homework exercise as well. Like I don't think I would be doing lead code. Had I started stream on time, I would have completed by 8 and done lead code. This is a good homework exercise. Uses the same idea which I used for problem day. So the main idea I have over here is like let's first populate some of the cells we have. Like in the first column, it says we have one cell. Like let me take some example as well. 10, 5. This is the cell at row 10, 5. Like I won't grow full grid. This would be the, let's say this is the cell at 10, 5. This is the cell at 4, 7. This is a cell at 2, 2. This is a cell, let's say somewhere at 12, 3. Let's say we have this cell at 14, 8. Like and like this is the final cell we want to reach. And this is 1, 1. So the idea is like use like sort it in them, like first sort all the points with smallest x coordinate, and if x coordinates are equal, smallest y coordinate. The idea over here is like the maximum number of coins you can start from here and reach with this cell taking this coin would be 1 when you directly come over this path. For 4, 7, the maximum coins you can get would be you go to 2, 2 first and then reach here with distance 2. For 10, 5 also it remains same. You reach 2, 2 first and then go to 10, 5 distance 2. For 12, 13 as well, like the maximum coins you can probably get would be 2 only. Go to 2, 2 first and then take. So basically the way you look at it is you basically need maximum on this path. Like how many maximum cells you can get from any node in this, and then you can go from that point left right to reach here. Or for 10, 4 also this holds true. Maximum everything here is 1. And for 12, 3 as well. But now when you want to look at 14, 8, like you should look at this grid first. This is a very giant grid. And you should look at what is the maximum value here. This is 1, this is 2, this is 2, this is 2. So you can take any of the 2 here and then from there go here to get 3 cells. Similarly, let's say if we had 6, 8 here, then the giant cell, this would have contained this part only, and the maximum in this is 2. So even to reach here, you would get 3. So this way you can try to find all the points here, and there is probably a technique known as sweep line. You can probably use that with the segment tree to get the maximum in this rectangle here. The main idea is since we sort by x coordinate, you don't have to really worry about the coordinates you have processed before it. All you have to look at is like you should only look at the coordinate you have processed so far which have y coordinate less than your current value. So like for example, first I start from here, then I go here, process for this. When I process for this, I only look at the y, all the coordinates that I have processed so far, which have y coordinate less than equal to 7. Maximum here turns out to be 1. 6, 8 would be the next one which I will go to. So I don't have to worry about x coordinate because I am processing in increasing order of x coordinate. All I have to look at is like only the y coordinate which have y coordinate less than 8. These two take maximum of them. Now 10, 5, like all the cells I have processed so far has x coordinate less than 10, so it's definitely up. But I should take only those coordinates which have y coordinate less than 5. So this is the only cell. Maximum 1 plus 1, 2. 12, 13 would be next. 12, 3 would be next. And like only y coordinate up to 3 would give me this cell. And 14, 8 would give me everything. So like that way we can first form a path which gives us the maximum number of coordinates. And then like once you know like you want to go to 2, 10, 5, you can either go right first, then down, or you can go down, then right. It doesn't really matter. It will give you the same answer. This ends up being the solution for problem F. To keep it a bit convenient, what I did was I also added point 0, 0 and n minus 1, m minus 1. I was doing zero-based indexing, sort everything. Create a segment tree with number of y coordinates here. Now for the reaching 0, like after I sort, notice that 0, 0 would be the first cell and the final cell I want would be the last cell. K plus equal to 2 because I have increased 2 coordinates. For all j from 1 to n. Since it's an increasing order, I look at what my current y coordinate is and what is the maximum number of cells I can take with any y coordinate from 0 to y plus 1. This is G, like this segment tree contains, first value contains what are the maximum number of coins I take, and second coin contains what was the index of cell I took over here. And like this index might be different from original, but it's fine. So whatever count I have got, I marked this as dp, like that would be the maximum count of coins I would be getting by plus 1. And then update this value by dp, like the new value we have. Once we are done with all the paths, just notice one thing, like this will end up taking this cell as well. So I should probably subtract 1 from the total maximum points I have taken here. And I now trace all the paths over here. So like now I can backtrack on the dp. The last point I would reach would be k minus 1 point, which would be this. So as long as I do not reach the first point in the sorted order, like look at what was the last point I took and from which coordinate did I reach at this cell. Keep iterating it. Now you reverse it in the decreasing order. You have got all the paths. So now print like the complete path you have got. So like reaching from, for every continuous pair of coordinate, that would be the path you would be tracing. So from path j minus 1, go to coordinate j plus 1. Now I have one coordinate here, one coordinate here. Just some method to keep a track of, like always I go up and down. First keep increasing x coordinate by going down, keep increasing y coordinate by going right. Whatever, once you have reached y, that is the string you should trace to reach from this point to the other point over here. And if you keep printing it for all the coordinate, print new line at last, and that ends up being the solution here. Any questions on problem F before I move on to problem G? For expected rating, you can probably look at Atcoder. So like this contest is yet to be updated with the rating. You can probably find equivalent Atcoder ratings here. So I will move on to problem G. Problem G says, as far as possible, you are given a tree with n vertices. The tree vertices are numbered from 1 to n. The ith edge connects ui vi with the length of li. For each k equal to 1, solve the following problem. Takashi and Oki play a game. The game proceeds as follows. First, Oki specifies k distinct vertices on the tree. Then Takashi constructs a walk that starts and ends at 1 and passes through all the vertices specified by OK. The score is defined at length of work constructed by Takasi. Takasi wants to minimize the score, and while OK wants to maximize it. Find the score and both the players play optimally. So what it has been saying is, like, first you are given a value of k. One of the player will choose k different vertices on the tree. Then another player will start from one and at one, and it will go to all the k vertices over there. And like the person who is moving his goal is to go to minimum possible edges over here. And while the person who is selecting vertices, they want to maximize the path this person will take after factoring account the minimum. So like let's probably look at some examples here before we proceed a bit further. One to two path length is 3. 2 to 3 the path length is 5. 2 to 4 the path length is 2. 1 to 5 the path length is 3. Let's say if we choose only one vertex, then what will the person do? If we choose 2, the person will go to 2 and come back to 2. The total path would be 6. If we choose 3, the person will go to 1, 2 and 3 and then come back via same path. Total length would be 8. If we choose 4, person will go to 1, 2, 4 and then come back via this path. The total length would be 10. If we choose 5, the person will go to 1 and come back. The total length would be 2. So the maximum we can get is by going to 4. No, wait. 1, 2 and 5. 8 to go down and 8 to go back. So the total here would be 16. So the maximum possible we got was to go to this vertex. So if we have to choose only one vertex, the best we can do is we can choose 3. So that the person goes to this path and comes back via this path. So for k equal to 1, the answer is 16. What can we do for k equal to 2? We have to choose one more vertex. You see, there is no point in choosing this vertex. The path remains same. So the extra path someone has to travel would be 0. While if we choose this, now when someone is going down, when they are coming back, they will have to go back to this, come back this, and then go back to 1 again. So the extra path here would be like whatever section was there, and extra 4 you will get, which would end up being wait 1 second, like did I created the edge weights correctly? 2 to 4. Okay, this is 3, sorry. Or if we take this as a second path, then person will have to go down via this path and then also come back here and go back here. So we will see an increment of 6 over here. So total count would be 22. So let's say on the second path we take this. The third time, like this is the already path edges using which someone is going on. If we take 2 as the third vertex, nothing changes, the path remains same. But if we take 4 here, when someone is going down, coming back, they will have to go here and come back here, then travel here, go back here, go here. So you will see an increment count of 14. So 26 would be the answer for k equal to 3. And for k equal to 4, you are definitely visiting all the vertices, all the edges. It doesn't really matter which you choose. You can just choose vertex 2 to get again 26 for k equal to 4. Or if you understood it by now, what we are seeing is like at any point of time, we have a set of edges we will definitely visit. We should choose the new point leaf node in such a way that the extra path you have to travel to go there is maximum possible. Or another way around, it says like we should choose k vertices. Like initially, let's look at the leaves only, because if you take some parent, you can also go to if one of the leaf in the child to go up to increase the length. And once you have already taken all the leaves, you would definitely visit all the edges. Now just randomly choose any vertex you want and your distance traveled would not increase. This was the first assumption. Now our problem reduces to choose k leaves in such a way such that the maximum distance traveled, like basically if you look at all the set of edges from root to that leaf, that set contains maximum edge weights possible. And the idea which I am proposing it, for the k equal to 1, choose the leaf which is at maximum distance from root. Now let's say we have removed all of these edges. Now for the second vertex, choose the new leaf which increases the number of edges which are not yet taken. In this case, it turns out to be this edge. Or like probably, where is my pen? Or let's say had it been 4 here, we would have taken this as the second leaf and this as the third leaf and so on. The idea in general works, and like this idea was used has came in code forces earlier as well. And like probably like I did not have a regress proof, like you can probably try to do it with exchange argument or something, and like let's see if Atcoder prepares on it. And like it happened that someone recently discussed this on code forces, flagging out this 2800 code forces problem does not have a proof, while like just choosing every time the maximum increment will give us the answer. So like the problem you see, the task becomes as follows: choose k minus 2 leaves, k or k minus, such that in a way that union of that part to root is as large as possible. And this can be done greedily. Take a leaf with the longest path, then keep taking leaf that has as many new edges as possible union possible. And then there is some implementation. Pretty much you can probably modify this code to get it work done for your case as well. And like this was the idea I had for this problem. Implementation, like few people had different implementation. I think my idea was neat, and that was the reason why I ended up doing much faster. So what I did was, like probably let's again draw the same graph here. This is weight 3. This is weight 5. This is weight 2. This is weight 3. Like for each edge, keep the longest weight from some leaf to it and keep one vector where the delta you can get. So for example, here we don't have any leaf. So the distance from maximum distance from any leaf to this node would be 0. We don't have any leaf here. The maximum distance from any leaf in this subtree to here would be 0. And if we extend this 0 part to this node, we will get one path of length 2, one part of length 5. My idea is like I will keep extending this weight 5 to go to root, and I will put this 2 in a vector somewhere. Like basically the increment edge weight delta I can get for 2 here, and this path only ends here. Like what I'm saying is this would be one of the increment I will make at some point in time. I don't decide when. And then for this 2 to 5, I keep the longest width and increment it over here, and I say like there is one leaf with distance 8 over here. Similarly for 5, the distance from any leaf to here would be 0. And for if I increment this 0 to 3 here, I would get 3 extra here. What I say is like for 1, I will keep this 8 as it is, and I will push 3 in my vector as well. And at last, when I am done with the root, I go over here, like this 8 is the longest path. I put it over here. The idea is sort them in decreasing order, 8, 3, 2. This would be the extra additional edge weights we would be getting. So the first time we want total edge weight would be 2 into 8 because we will travel it as twice. Second time we would be able to create extra weight of 3 over here. So the total distance would be 2 into 11, 8 plus 3. Third time the extra distance we would be able to add by increasing one of the node would be 2 only. So the total distance traveled would be 2 into 13, which would be 26. And you can probably put 0, 0 more over here. So the next time also 26 and so on. The code is quite short. And this ends up being the solution for this. DFS U to be like this returns the maximum distance up to root to reach this node. for distance equal to 0 0, what is the maximum distance from child to up to child, and if we add this node here, that ends up being there. If maximum distance to reach the child is more than what current distance we have, just put it in our vector here and continue. Otherwise, put whatever previous distance we had and assign the new distance we have got as child and return this new distance over here. And at last, this function will also return maximum leaf distance from leaf to over here also. So put it here, sort them in decreasing order. Now these are the increment deltas you have got over here. So like you can probably run prefix sum to get the total edge rate. Like now you know all the delta for each step. Taking like sum of first largest 5 delta will give you maximum distance if you choose 5 vertices. So a prefix sum kind of thing over here. And like bj would be the maximum distance if you take j plus 1. It's a bit 0 based indexing, but 0th index denotes if we take only 1 leaf. First index denotes if we take only 2 leaf, and so on. So print double of those edge weights and you would be done. So this was my idea for problem G. Like the important thing which remains over here is like how do we prove that always taking maximum we can will give us the final answer. Like probably let's say if Editorial proves it. For me it happened to be like I discussed this problem, code forces problem, with someone on Discord a few days ago. So this ends up. So I definitely remember this grid should work here. So I think these were my solution ideas for this problem. Any questions on any problem before we call it a day today? And thanks everyone for joining today. Like do while part is the way to generate all permutations. Like this is next permutation standard library function which ends up giving you the all permutations, and that's what I was doing over here. So the assume is like this do and this while with next permutation loop, and every iteration of loop will give me a different permutation, and this will iterate on all the permutations as well. So once I am inside the loop, I have one fixed permutation. I want to do something over here. Like why permutation was needed? Like the idea is like you have to visit 5 different visited, and there would be some order using which you will visit 5 per bridges. Like and to ensure that you go through all the checks and take minimum for each of them, what I try to do is I fix one order of a permutation and then try to see what would be the minimum length for this order if I want to visit bridges in this order. And if I try all the 5 possible orders of bridging the bridges, whatever minimum I have got would be the in fact the minimum to reach some of the vertex here. And like I slightly agree, like when you are visiting from shortest path from one bridge to another, it can be possible that you have bridges one of the taken bridges. But if you are trying all 5, minimum you get will ensure that you visit each bridge only once, not more than that. And Floyd Russell was algorithm I used was to find minimum distance from U to V in order and queue. So any more questions on any of the problem before we call it a day today? Like I think like 10K special stream is around 1 hour or so. like I don't really have an agenda for it. Like probably I will answer some questions from the chat and that would be it. So yeah, like let me just send that code forces problem link as well. Like this was the code forces problem. So like thanks everyone for joining the stream today. I think we would meet again in an hour or so. And I will end this stream now.